our various RAID types, a volume manager overview, file system overview, section 2, ZFS 101, copy on write, the ZFS storage hierarchy, and then finally in section 3, we're going to go over how ZFS storage is managed within Houston itself, what is Houston, and the Houston modules. So starting on RAID here, and apologies if I am talking a little bit quickly, it's not one of my strong suits to slow down, especially with the amount of coffee I have in a day, but that's neither here nor there. So going into RAID. So RAID combines 2 or more drives to act like one singular device. As you can see here, you have a RAID 0, which is very, very good for heavy read operations. It's many, many disks that present as one, but it's also known as scary RAID because you have no redundancy with RAID 0. A RAID 1 excuse me, RAID 1 are mirrored VDEVs. So blocks mirrored, you have no stripe, no parity. Your RAID 5, which is 1 drive of parity per VDEV, RAID 6, which is 2 drives lost to parity per VDEV, and then you have your RAID 1+0, which is storage devices that are mirrored and striped. So going into the volume manager, it is what joins multiple RAID groups together. A group of RAIDs allows for data to be presented to the end user. There we go. Not sure what happened there, but so going into a volume manager, as you can see here, we have our grouping of HDDs. We have 2 of them here. 2 RAID, let's just call them a RAID Z2. So we have 2 disks here that are lost to parity, and they are grouped together into one pool, which we'll get more into the ZFS terminology as we go through. But this is presenting as one big pool or one big namespace of storage to for your clients to see. So that brings us into the file system, which is another great part of ZFS because, as I did not mention, that the ZFS is a combination of a LV, logical volume manager, and a file system. So all user file access is through the file system and organizes the blocks into a coherent file system with files and directories. So if you're familiar with things like Mac's Finder or Windows File Explorer, think of it in that way, just a large cascading group of folders, files, subfolders, and whatnot. So that brings us to the crux of today's topic, which is ZFS and what it is. So as mentioned before, it merges a traditional volume manager and file system, and it uses copy on write to as a transactional mechanism. And we'll get a little bit more into copy on write as we go through the slides here. So with ZFS, it has a lot of great features that are not typically offered by your traditional storage systems. So you have snapshots, inline compression, instant pool creations. If anybody here is familiar with MD-ADM, you know the pain of building a pool or adding a storage array to that. No RAID hole or aka write hole worries, and built-in self-healing with ZFS scrubbing to prevent against things like bit rot, to keep your data intact, kind of a set it and forget it sort of mechanism to keep your data safe. So copy on write. Copy on write, it creates a copy of the block of data for each write operation. So every time there is a write made, or let's say a deletion that's made, changes are made to the copy rather than the original. So the metadata is updated within ZFS, within the file system, to point to the newly written blocks. And this allows for RAID hole protection, snapshots. So those are a point in time reference of your data, which can be set to run automatically, to retain for a certain amount of time. And if you ever need to completely roll back in the event of a malicious attack, file deletions, anything like that, makes it very, very easy to retain and retrieve those files. And again, instant pool creation. And ZFS storage hierarchy. So at the very tippity top of it, you have the Z pool, which is kind of the amalgamation, kind of what holds your VDEVs, your data sets, your individual disks, everything. So it's one or more disks that are grouped in ZFS terms, also known as a VDEV. And then VDEVs, also known as virtual devices, they are a single disk or multiple disks that are paired together and are presented as a single namespace within ZFS. So VDEVs within ZFS, you have two main types. You have your support VDEVs, which are your cache, log, and special VDEV. And then you have your storage VDEVs, which are your RAID Z, your mirror, and your single disks. So ZFS storage hierarchy. Each pool requires one or more VDEVs, one or more storage VDEVs. Fault tolerance is handled by the VDEVs themselves. So if you have a mirror, the great thing about that is very, very fast, very speedy, great for heavy IOPS operations, but you lose half of your storage efficiency to parity. Now with RAID Z2, it's great for very large files, very large sequential writes. You lose 2 disks to parity. It's a great sort of middle way between having good performance and having that storage integrity or that storage retention and security that you need. And so when a disk failure occurs, the Z pool rebuilds the VDEV at the VDEV level rather than the entire pool. So with that, you have a pool that, excuse me, you have a pool that only rebuilds the data that is present. So a less full VDEV will resilver faster than a full one. So it's kind of like, you know, on Windows, when you see your C drive is getting to 99% full, that red bar is almost fully complete. Everything kind of slows down. It's kind of the same thing with ZFS. So the less full it is, the faster rebuild, the faster your performance will be, as it doesn't have so many checksums, things like that to do. But that's kind of getting into the nitty-gritty of things. Continuing with storage, ZFS storage hierarchy. So what type of VDEV should be used? And this is very dependent on your specific use case, your workflow, your data size, data size. So RAID Z2 is the most common in large, dense storage arrays. For best storage efficiency, it gives you 80% efficiency, excuse me, best resiliency. Any 2 disks can fail per VDEV, and you can still rebuild your pool. So let's say you have an XL60 full of 20 terabyte disks, and you have 6 RAID Z2 VDEVs of 10 disks apiece. So you can lose 2 on every one of those VDEVs. So you can lose a total of 12 disks as long as they are spread out between those VDEVs, and you'll be perfectly fine. I mean, not fine, you're probably don't want to get to that situation in the first place, but you know, you'll still be able to read and write data. Your data will still be there and intact. Then you have mirrored VDEVs. So they're only deployed for very specific use cases. So as mentioned before, only 50% storage efficiency. You can't lose more than 1 disk per VDEV. Excuse me. So mirrored VDEV is great for things like I mentioned, virtualization, anything that has is very, very IOPS intensive, are more designed for VDEV operations, or VDEV arrays, I should say. And how big should your VDEVs be? So typically in the past, we used to size them to, again, using the XL60, we used to use a 15 drive VDEV, and that was great back in the day when, you know, there were 10, 12 terabyte drives max, and those were massive for the time. And now we're getting into 20, 24 and upwards, and doing 15 in a RAID Z2 of 24 terabyte drive VDEVs, great for storage efficiency, but as you start to fill this up, resilver times and rebuild times become exceedingly long. So we've recently gone to 15 disks if it is, you know, on the smaller side, like 20 and under, but above that, we'll usually stick to 10 or some certain, or an even divisible number that, depending on the amount of disks and the amount of slots within the storinator or within the storage system. So small VDEVs, as mentioned before, can give better IOP performance, but not too small, so you lose a lot of raw storage space to redundancy. Again, 50% is lost to parity within a mirrored VDEV within a mirror pool. So expansion, very, very easy within ZFS. Again, instant VDEV addition, similar to the addition of, or the initial creation of the Z pool. With that, it is just selecting the same number of disks, preferably the same size. You can go larger, but that added space or those added terabytes are not going to be recognized. The disk is going to be recognized as the size of the previous VDEV. So if you have, let's say, a 16 terabyte disks in your first VDEV and you put 18s in, it's only going to recognize those 16s. So each additional top level VDEV, it'll increase the IOPS and the performance of your systems. If anybody has seen the most recent video from Mitch Hall on our channel, it is a great deep dive into IOPS and the myth of getting the performance of a single VDEV's IOPS per VDEV. So performance implications. This is always a big topic when it comes to ZFS or any storage system, really. Mirrors, this is when you're dealing with, as mentioned, small IOPS, small random IO workloads. Write speeds are limited to the slowest drive, which is why we always like to keep things homogeneous between the VDEVs, the Z pool itself, and each of the individual drives. And RAID Z, great for sequential writes or any other general use workload like a general file server, backups, anything like that. That's a day-to-day operation. And IOPS on this are limited to the slowest drive as well. And going into our support VDEVs or special VDEVs a little bit more. Actually, we will in a second, because right now we're talking about ARC. So the ARC is a purpose-built read cache that's stored primarily in your system memory. It's unique to the ZFS file system. The ARC algorithm, it's used for caching. It's designed to avoid cache thrashing that occurs with traditional file systems. It provides statistics to qualify the ARC hit-miss ratio. So with the hit-miss ratio, typically the lowest you'd really want it to go before you start considering, okay, I should probably add more RAM to my system if possible. 90%, there's people that say 95. I mean, typically you don't want any misses, you want 100% hits, but of course, with workflows changing and everything, that might not always be possible, but a high miss ratio indicates a undersized ARC where adding more RAM to the system can definitely be beneficial. So support VDEVs. They're not required for a Z pool to function, but they can help in certain scenarios, depending again on your workflow, your data type, everything like that. So starting with the cache VDEV. This is your L2 ARC VDEV. It's a read cache only. It won't accelerate your writes at all. This is the L2 ARC or level 2 ARC. It's built into, it's usually put on a faster medium like SSDs or NVMEs because it is meant to act as a kind of a, let me use a little bit of analogy here. So you have your desk here, you have desk absolutely full, can't fit anything else on it. The desk is your ARC. You have your table over here, bring a little table over, this is your L2 ARC. Well, it's not as big, it's not as fast where you can retrieve things, and I'm stealing this analogy from Brett, who had done this exact thing a few years ago, but it's great for this occasion. So you have your table, you can grab things very, very easily, but you ran out of room. The L2 ARC or level 2 ARC is you can go over here, you can grab something from this table, and it's not as fast as grabbing it from right here, but it's still very, very fast compared to things going to soft space or going to a slower medium. So if Z-pool ARC does not have a high miss ratio, then an L2 ARC will likely not benefit. So that means that everything is within the ARC or within memory, and I always say that, and most people I think would agree, that you should always max out your RAM or add more RAM before adding an L2 ARC. So there are some caveats with it. An L2 arc requires some arc space to store the index, which is one of those reasons why you should add more RAM before you go into getting an L2 arc. So with that, it using a certain amount, you can have diminishing returns, and the kind of ballpark of the average is 3 gigabits of arc per 1 terabyte of L2 arc. And next, that brings us to our log VDEV. So remember how I mentioned that ZFS writes are transactional? When ZFS writes a block of data, temporarily stores that in the ZFS intent log or the ZIL. So before writing them permanently to the disks. And this allows ZFS to replay writes if the file system crashes due to sudden power loss. So let's say that you have some data in flight. There's a power off, there's a say a storm hit, something like that. You have I think it's about 5 seconds of writes in flight that can be lost, but with this living in the ZIL, excuse me, it's always present on the ZIL will prevent that from happening, essentially, is what I'm trying to say. So the ZIL is always present on the Z pool, and by default, it's stored directly on the disks themselves. So the logged VDEV allows for the ZIL to be placed on a fast device rather than the disk, so increasing write performance. And it doesn't have to be very large. About 5 gigs is sufficient, and it should be mirrored because a ZIL failure could result in a small amount of data in flight lost. And lastly, that brings us to a little bit of a newer VDEV in the ZFS world. This is the special VDEV. So it's used to store metadata and small files on the special VDEV. Can dramatically speed up random I/O as metadata is read off the flash rather than spinning disks. Listing files and file crawling will be significantly faster. So if you have a very, very deep file structure, hundreds or thousands of nested folders and files within your file system hierarchy, that can take a long time to actually populate and can really slow down your workflow. And that's where the special VDEV really shines. And this absolutely needs to be a mirror because this is what stores your metadata. This is what stores the data about your data. So if that's gone, your data is essentially lost. It doesn't know anything about itself. It's essentially like it has amnesia and it cannot find its way home. So once it's added, it can't be removed without rebuilding the entire pool. So how is data organized within a ZFS storage system? At the lowest level, we have sectors. So a sector is the smallest physical unit that can be written to or read from the underlying HDD. Blocks are the next level up there. So all data is stored in blocks. Maximum size of a block is defined for each data set, which we'll dive into. If you have multiple use cases, you can really change each or set each data set for that specific use case. And then it's very similar to a mounted file system. It appears as though it's just another folder within your either, let's say, going back to Finder or Explorer, and presented as just a network folder. And they have their own underlying properties that are either inherited from the Z pool, or they can be their own, have their own characteristics and properties. So what features does ZFS copy on write offer? It offers RAID hole protection, snapshots, replication, and inline compression. And going into a little bit more of the unique features of ZFS, you have instantaneous pool creation, hybrid storage pools. So you can have pools that you can have SSD pools and HDD pools on the same system. You can have, again, special VDEVs or any VDEVs that are make use of faster SSD media to really speed up the performance of your system. Built-in checksumming for data integrity. So that goes back to the scrubbing and checks of data integrity that I mentioned previously. Fast RAID and device rebuilds. built-in geo-replication for disaster recovery, native file system tools to safely and efficiently move your data from one ZFS system to another. So things like Znapsend, which is the tool that we primarily use for doing ZFS replication to remote systems. So everything that we covered today, we went over zpool and the facets within that, the VDEV, your storage support, storage and support VDEVs, your ARC or adaptive replacement cache, datasets, blocks, and sectors, unique features of ZFS, and copy on write. So going into ZFS, going into 45 drives, and when it comes to ZFS, Ceph, Proxmox, ransomware, anything, you name it, we're your single point of accountability. We have one-on-one consulting or in teams, hundreds of resources like our public-facing knowledge base, various articles with our customers, blogs, videos. Speaking of video, seriously, go check out that one that Mitch Hallhead did. It is fantastic. And not just saying that because I work here. Maybe a little, but fully integrated, easy to use storage control UI that unites hardware and software. So going into that, uniting the hardware and the software, that brings us to the Houston UI. So the Houston UI, it's easy to use, easy to navigate. It doesn't have a lot of the added bloat or unneeded features that a lot of other web-based UIs that we've seen typically have. So it's for everyone from your entry-level administrator to your experienced administrator. And as somebody who started here at 45 Drives about 3 or more years ago now, I'm losing track, I think it's closer to 4, but I had started here, I had no previous experience with Linux, let alone ZFS or Ceph. I had less knowledge than an entry-level administrator. I was here at the beginning of Houston, and I got to see it grow over the last few years, and it has just become easier and easier and easier to use. But that's enough of that. So you can directly integrate with your 45 Drives hardware, which we'll see in a few moments here, powered by the Cockpit project, which is a great open source project that is, the source code is available on GitHub, obviously, engineered to give you all of the system information and tools you need without any clutter, as mentioned, flexible so it can adjust to any additional requirements you may need. So diving into a little bit of the Ceph dashboard here, Ceph dashboard, ZFS dashboard. Been dealing a lot with Ceph today, so it's been on the mind. When you first log in here, you will see the overview page. So you can see things like the general health, if there are any bug fixes or updates available, any services that have failed, your resource usage at a glance, so CPU and memory, system information, which will be great if you have to open a support ticket with myself or any of my colleagues in the support department. We'll be able to get a view of your system before even connecting. Going into the ZFS tab. So going in and creating a pool for the first time, very, very easy. All you do is you click Create Storage Pool. You go in, you select the name of your pool, the type of virtual device. As you can see, we have a RAID Z2 here. Then you would select your disks. Sector size is one of the things. Doesn't really change unless you have a reason to change it, which not too many, but there are some. Record size is one of those things that absolutely we will change and can change depending on the kind of tuning that we want to do to the system and the general workflow that works best for you. Deduplication, again, one of those things off by default, and the defaults are default for the reason is I'm sure some people have heard before. Reservation, which I always mess up the name when I first say it, but this is kind of a small buffer zone, an area of the pool or VDEV that can't be written to, and this is adjustable, but 10% is usually a good point not to make any smaller, because think back to where I mentioned about the your C drive on your Windows system or your Mac. When it fills up, everything starts to come to a crawl. It's kind of the same thing with ZFS or any file system, really. It is going to suffer when it gets to that critical tipping point, and that's what this reservation is for, to make sure you don't hit that portion inadvertently. LC4 compression, and automatically exploring the storage pool. So this is kind of what you're going to see when you initially create the pool. These are the defaults. The only things that you really change besides this are the name of your pool, your virtual device, and the disks. And record size, 128 is usually good for most use cases there, but where specific performance needs are needed, record size can be changed to meet those needs. So let me go back here. So as we can go through, you can see here that we have our test pool created. And then when we go through, we'd also want to attribute or add a file system to it. So you can see here we have our test pool, and then underneath that we have test FS. And we can see the available storage, the reservation up top on the top of the pool there, our record size, dedupe, if it's shared, if it's mounted, and if there is replication on it. Now, going into file sharing here, if we're using, let's say, SMB, and we want to create an SMB share to share to our Macs or to our Windows system, it's all done through here. It can either be done with local users or Windows AD users and groups. Both very, very easy to set up, very streamlined. So in here, you would just go create your test share, create the path for it, add your users and groups. And as you can see here near the bottom, we have macOS share optimizations, which clicking this button helps with things like file system crawling, overall performance of the of an SMB share when connecting to Mac. And then also we have NFS as well. Very, very easy to set up. Again, just give it your share path, the host, and the settings that you want for it. Click apply, and then you have an NFS share ready to go. So what happens when you have a disk that fails within your ZFS storage pool? So you have disk 2-11 on RAID Z2-0, 0 indicating your first VDEV within the pool. It's offline. So what do we do in that case? So we can see that the pool is degraded. It's 2-11 that is offline. So from there, without us having to even go and into the terminal or to the data center, anything like that, we can go to the 45 drives disk tab here, which is one of my favorites that's been developed in-house by our R&D team. When you go in, you would click on your specific disk that's having issues. It'll tell you what VDEV it is part of, what pool, if you have multiple pools within the system. It'll give you the smart details, so you can see the disk type, the serial number for any RMA purposes, its power on time, temperature. So it gives a lot of great information that you would need for troubleshooting or verifying if a disk replacement is needed, or if an issue lies upstream or with more disks within the system. Next is the motherboard tab. So this is an interactive menu or overview, I should say, of the motherboard within your specific system. So if you go over and let's say you have a you want to figure out the model of your HBA or your NIC card. So you can go over, you can hover over the cards that are in the system that will populate. You can see we have an HBA, it's a 9305, 24i, we can see which bus it's in, and it's the same thing with the RAM, CPUs in the system. So you can see the manufacturer, you can see which DIMM it is, so you don't have to go peering between the slots to see which actual DIMM it is, or gather up the old manuals for the Supermicro board or whatever board you have in the system and figure it out from there. Very, very easy to do right from the Houston UI. Then the 45 drive system tab is kind of an extended view of the 45 drives motherboard tabs. So you can see the CPU slots, what's available, the bus address again, network card, what's in there, the model. You can also get the chassis size, serial number of your system, the type of motherboard that's in it, and the serial number of that motherboard. And again, a lot of great information like RAM, so manufacturer, the size, if you have a drive a stick of RAM that is out of the system, you can see here which one is no longer showing, and really makes things easy for troubleshooting and replacement purposes without having to go to the data center, go to the storage closet and crack it open and see what's going on with it. Then mentioned that the disk tab is one of my favorites. This is probably my favorite. It's something that when you think of a storage system, you might not think, oh, this is not too big of a deal. We have this on Windows, we have this on Mac, and Linux desktops, but it's not typically something you see in a lot of web UIs that are primarily for storage systems. So this is a built-in file system navigator, purpose-built by our R&D team. The project was taken up by somebody in our R&D team. It had a few attempts beforehand, I believe, so it didn't really go anywhere. But then our team took a look at it and made this lovely navigator tab. So you can go in, you can see the actual all the directories of the Linux storage system itself, or you can actually go into your pool. As you can see here, we're in demo pool, testfs. That is this is kind of like I mentioned before, where you have it's just presented as another folder icon right there. That's how it'll essentially be presented to your clients for access. And talking about end-to-end support, this is my neck of the woods. So we have a full support team that will help you from decision-making, design and deployment, and ongoing maintenance. Ensure you get the right storage solutions for your needs. We'll support both the hardware and the software and the open source software. We have 24/7 emergency assistance, a 3-hour response time, dedicated emergency support, in-house support team, integrated remote training available, and consulting services available. And just to briefly touch on SnapShield and the scary world that we live in now of ransomware. We hear about stories of it every day. Can't really get away from it in this day and age, but SnapShield, it's a ransomware activated fuse. It's an agentless software that runs on your server, listens to client traffic. We also do Linux hardening, so restrict root access. We configure the firewall to only allow what is absolutely necessary, two-factor authentication, etc. So SnapShield is meant for deployment with Samba or SMB, and we'll pop the fuse if there's any sort of malicious attempt on that data set. We'll also implement monitoring and alerting, so you'll get alerts if there is any sort of malicious attack that is picked up by the server. We'll run fire drill scenarios to make sure that the system is operating to spec and that you have full confidence that you can administer and know the plan to reach out to us at 45 Drives if need be. We'll ensure that your data is recoverable, locking down your servers. You'll detect ransomware based on file system patterns within seconds. So with SnapShield, it will, it will, as it lives on your file server for longer and longer periods, it'll pick up the general data flow of your systems, be able to learn from that and learn what looks a little bit off, if there's a lot of writes coming through, like an obscene amount of writes, or file changes happening to the system. The fuse will be popped and access to that server will be cut off, and that's where we come in. We can ensure the data is recoverable, which due to having snapshots on the system, it absolutely will be. And we can have restoration with shadow copy if need be, so something a little bit more based on the Windows side. This is a lot of people like to call it the break page. I haven't come up with a better name for you. Not that it really is one, but it's kind of a page to just show how far we've come and how many places we actually are. So you can see here, Yale University, well, a lot of universities, really a lot of the top ones in the US and Canada, HBO, Intel, Amazon, Backblaze, on and on and on. And this is just a very small sampling of who we're with, but at the same time, we're with a lot of these big companies, a lot of these big organizations, but we also want to, we also have a lot of people in smaller video production, small offices that we support every day, and I myself work with on a daily basis. Resources, so we have our YouTube channel, our public-facing knowledge base, private webinars, customer case studies, and storage articles. Talking briefly on clustering. So what happens when you have your ZFS server, or you know that you're going to have a need for rapidly needing a lot of storage, or if constant uptime is critical to your organization and your organization's success. That's where clustering comes in, where it allows you to do incremental updates to the amount of storage you have in your system and allow for a highly available system that can withstand multiple instances of entire nodes, entire racks of systems going down, depending on how large the cluster is. So you can get an instant quote online at 45drives.com. And with that, I will open up the floor for questions there. And let me bring this up on my end, stop sharing my screen. All right, let's see. All righty, so let's make this a little bit bigger on my end here. All right, my colleague Patrick is in the chat right now. I see he's already answering quite a few of you there. So let's see. Any upcoming plans for it since Bob Henderson? Has Houston been updated or planned to be updated for Ubuntu 22? It's not been configured. With that being said, it should work, but may have some issues with certain modules. Any upcoming plans for it since 2004 drops next year on standard support? Same with Alma and Rocky 9. So Ubuntu 22 is definitely on our plans of things to roll out and implement. There's just a lot of moving parts to it that we need to make sure that work with all of our tools, work with what we do to deliver a cohesive sort of system for more or less words. But yeah, 22 is definitely on our roadmap there, because we definitely want to be up to date and be on the what is currently available and what's currently supported with Ubuntu and Rocky. And I'm just going to make sure that there are let's see. All right. Oh, there we go. Following up on Houston's support question, would it maybe make more sense to target Ubuntu 24 since it's about to release? Is there a roadmap somewhere of what distribution Houston has been validated with? Happy to hear you mention Rocky, thanks. Yeah, we're big fans of Rocky Linux here. That's actually not a bad idea. I don't have the information off the top of my head on if they're planning on going to 22 or sticking with, or going to 24, or they're going to be sticking with 22 there. That's something that I'd probably be able to get more information for you if you'd like there, Steve. I can reach out to you after the seminar here and see if I can find some answers on that. All right. And we'll take a few more questions there before we wrap things up. Let's see. Any support, et cetera, coming to D-RAID in Houston? Ooh, interesting question. So we do have a new module for ZFS incoming very, very soon. Now, if that has D-RAID support on it, I'm not too sure myself. I haven't dived too deep into it, but that is something that I can find out for you there, sir. So let's see. A few more questions. If you have a customer that does streaming, what kind of ZFS setup? Ooh, let's see. There is. If you have a customer that does streaming, what kind of ZFS setup would you use? So that's really dependent on the specific use case and everything that you're doing. Like, understand that it's streaming, but with things like the bitrate involved, the type of streaming, things like that. It's one of those things that's really better saved for a call with a architect and a one of our account managers who can really understand your needs and get you exactly what you need. All right, let's see. So what time have we got here? 45. We'll leave the floor open for questions for another 2 or 3 moments there, and yeah, we'll see what we get. How do you determine how large a special VDEV should be? So with that, it depends on the general ingestion of the size of the files that are going to be on the system and the size of the Z pool itself. So depending on the size of the drives, the VDEVs, your VDEV array, really, record size, things like that. There's many factors that go into how large that special VDEV should be. Hey, thank you, Stephen. With disk getting faster, NVMe, etc., how does ZFS scale performance-wise? I don't see L2 ARC being as impactful with all flash workloads. Yeah, that is that's an interesting point you bring up. So with something like that, don't know off the top of my head if there's many use cases that would benefit from an L2 ARC. Not that it'd be to the point where it'd be make a very large difference. Again, with an L2 ARC, having maxing out your RAM is always the first thing you should do before implementing an L2 ARC, in my opinion. But that is definitely an interesting thing that I'm interested to see. We can do all the in-house testing and everything that that we want here to, and other companies can do as well. But we won't really know the types of performance that are possible until we get to people-specific workloads that are very general, very specific to them. So there are some that we can kind of make a guess on, like any high IOPS performance. If depending on the performance that required there, who knows? Might be something that L2R could benefit, but at the same time, it's you have NVMe. Where do you really go from there? But yeah, that's a good question, Bob. and actually expanding on that a little bit more. So L2ARC is one of those things that's great for being impactful when it comes to Rust drives mainly. Now, mind you, can be impactful as well for SATA SSDs, like offloading that to the creating an L2ARC that's on NVMe. Then you can see more of an impact. But yeah, I agree with you. I don't know how impactful it may be with all NVMe. It's definitely interesting. All right, what have we got? All right, we're just at about 10:02, so leave it open for another moment or so, answer any final questions, and then I think we will call it a day. I'd just like to say thank you to Patrick for answering the questions while I was doing the seminar here, and to Ashley in marketing for the helping me get set up here for doing my first solo ZFS seminar. And yeah, I think that is about time there. So yeah, thank you for joining us today, everybody, and hope you have a great rest of your day. All right, see you now.